Well, greetings and welcome to the Law of Conservation of Mass. So, the Law of Conservation of Mass in some arenas is also called the continuity principle. Though there may be some intricate differences between them, is a fundamental principle at Iron Range Engineering in our thermodynamics course. It's also a fundamental principle in fluid mechanics. It's also a fundamental principle in our physics courses. So this is a very essential principle. It's also a very easy principle. Another name for the law of conservation of mass would be performing a mass balance. If you're watching this video in our thermodynamics course, we've already done an energy balance. Well, mass balance is essentially the same thing. Basically, you start with some initial mass, and you can bring some mass in, or you could take some mass out, or both, or neither. And when you're done, you have some final mass. Um, I often think of like a bathtub. So you've got a bathtub, and your bathtub has a water faucet, and your bathtub has a drain. So there are lots of different ways you could do this. You could say, well, I start with my bathtub empty, and I turn on the faucet, and I run a whole bunch of water. So that would be, this is 0. This is bringing a whole bunch of water, leaving my drain closed. How much mass do I have afterwards? Whatever I brought in. Or maybe we go a little more complex and we could start with some initial mass. Ooh. And then we bring in a bunch of water. And then some little kid opens the drain and we let some water out. So we start with some initial mass. We bring some in. We take some out. And we end up with some final mass. I often think of this kind of like my savings account, or you rich college students with your savings accounts. You start the beginning of the month with a bunch of initial mass, some initial balance, got some money. And then mom and dad, of course, have some automatic deposit and they put a whole bunch of money in. And then, oh, you have to pay your bills. You go to the movies, you go to the Dairy Queen and buy your favorite teacher, Blizzard. You pay for your cell phone bill. And at the end of the month, you got some final mass. So balancing mass in a system is just like balancing your checkbook, or just like performing an energy balance. So let's take the equation and add one layer of complexity. As we've talked about in our thermodynamics class and in the previous video on mass flow rate, there is this thing called mass flow rate. So I've got some initial mass. Let's use a tank. Oftentimes there are tanks in engineering, and my tank has some initial mass. And then I've got a valve, maybe 2, and I open those valves and I have some mass flow rate in. So maybe we call this mass flow rate in 1 and mass flow rate in 2. So I'm going to say plus the sum of the mass flow rates in. And oftentimes in a tank, you'll have a valve so that mass can leave. So let's call that mass flow rate out. And if we only have one, but for our equation to be good, we would use the sum in case there are more than one. And if there is only one, well, the sum of one is itself. So mass flow rate out. And after a certain amount of time, we would have some final mass. And a typical engineering problem might read, well, you've got some initial height, and you have this much mass coming in, this much mass going out, and how long until the tank overflows? That'd be a typical problem. But speaking of problems, I seem to have a problem with my equation. I have a unit problem. I'm adding apples and crab apples. I have pounds and pounds per second. That's just not going to fly. What could I do? Oh, good idea. I could multiply the mass flow rate coming in for the length of time that it comes in. And the mass flow rate going out times the length of time that it goes out. Oh, that would be better. Then I could have pounds mass plus pounds mass per second times seconds. Oh yeah, this is good. Minus pounds mass per second times seconds equals pounds mass. Oofda, yep, it works. Well, this is the law of conservation of energy. Wait, excuse me, the law of conservation of mass. That's it. I can see the wheels turning. And you're wondering, oh, what would that equation look like in steady state? What does steady state mean? Well, in this example here, steady state would mean that the level in the tank stays the same. That the mass initial and the mass final are the same number. And so we could cancel them out in this equation. And in fact, we could cancel out the time if we were in steady state. And we would just get that the sum of the mass flow rates in equal the sum of the mass flow rates out. That would be the law of conservation of mass in steady state. I call this the gazintas equals the gazadas. And it's very useful. If you have a pipe, you'll see this on the FE exam every once in a while. You got a pipe and it splits. So you have a mass flow rate in, mass flow rate out, mass flow rate out, a 1, 2, 3. And they might do things like give you the density at 0.1, the density at 0.2, the density at 0.3, and the diameter at 0.1, the diameter at 0.2, and the diameter at 0.3, and then give some information like, well, if the water at 0.1 is flowing at some velocity, now we have enough to get the mass flow rate, rho A V, rho, get the area V, so we'd have the mass flow rate in. So if it's flowing at 100 feet per second at 0.1 and it's flowing at 3 feet per second at 0.2, what's the velocity at point 3? And you would be down to one equation and one unknown. You'd say, well, let me just go ahead and write it out. You would say that the mass flow rate in, that's 1, equals the sum of the mass flow rate out. It's mass flow rate 2 plus mass flow rate 3. And remember now, mass flow rate is rho AV, density, area speed, rho AV, and rho AV. So we have 3 densities, 3 areas, 3 velocities. In the example, the way I drew it, so there are 9 things, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of those 9 things, well, we only have one equation, so we can only find one. So 8 would have to be given. And that's kind of the way I've said, well, we know this, 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 and this. We know this, 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 and that. What's the velocity? So this is a common fluids type problem. You'll likely see it on the FE exam. If you have water, liquid water is called incompressible. And what that would mean is that the densities would be the same everywhere. So you could just cancel the density. Area 1, V1, area 2, V2, area 3, V3. All right, so there's conservation of mass. Thanks for watching. If you're one of my fluid students, you're probably watching this. If you're one of my thermo students, you're probably watching this. If you're one of my physics students, you might be watching this. So this is the law of conservation of mass. And I bet you're wondering about the hat. This hat is Lulu's dress-up hat. Lulu is my granddaughter, and when she comes to visit, she likes to wear this hat. And I'm feeling a little sad missing Lulu today, so I thought I'll wear her hat.